Let us get started with example on rectangular section. Last time I have mentioned that the boundaries of the cross section can be expressed in terms of this boundary is x is equal to a, the left boundary is x is equal to minus a. Similarly, this boundary y equal to minus b and the top boundary is y equal to b. So, noting that we can write a function phi as x square minus a square into y square minus b square, and we add one constant m. This ensures that the phi function is 0 all over the boundary. Now, I would like to take up the steps to find out the constant m. T is given by 2 times integration of the function phi over the domain here. The limits of integrations are minus a to plus a, minus b to plus b, x square minus a square into y square minus b square dx dy. Since the limits of integrations are constant, we can write, we can do the integration of this function with respect to x, this function with respect to y, and we get x cube by 3 a square x minus 8 to plus a. Similarly, y cube by 3 b square y by b square y minus b 2 plus b. So, this will give us a cube by 3, this will give a cube. So, that will give us a cube by 3 minus a cube, 2b cube by 3 minus 2b cube. So, this will give us minus 4a cube by 3 and this will give minus 4b cube by 3. So, that makes it, of course, we have left out the constant here m, so that m is carried forward. So, we have 2m into 16 a cube b cube by 9. Therefore, constant m is equal to 90 by 32 a cube by b cube. So, if you substitute back the value of m, phi is obtained. This is 90 by 32 a cube b cube into x square minus a square into y square minus b square. Let us now calculate the stress which is going to act at the boundary, particularly we will be interested in calculating the stress at the end of the x axis. So, that stress is going to be tau yz, and this is given by minus delta phi delta x. So, we are interested in calculating this stress at the end of the x axis here, which is nothing but x is equal to a, y equal to 0. So, let us calculate, if we indicate this point as a. So, tau yz at point A is delta phi delta x for y equal x is equal to a, y equal to 0. So, let us see tau yz at A is equal to 9 T 32 a cube by b cube, and when we differentiate this we get 2x y square by b square, and we have to substitute the value x is equal to a, y equal to 0. When we do that, 90 32 a cube b cube, this is 2a and this is minus b square. So, what we get is 9 by 16 T a square b. So, the stress at the end of the x axis is 9 by 16 T a square b, and this is approximately equal to 0.56 0.56 T by a square b. When a equal to b, then we have a square cross section. So, the stress at the point for a square section is 0.56 T by a cube, and it is known from exact analysis of this problem, the answer is 0.6 T by a cube. So, this is the exact solution. So, you can see that we have got the results quite accurately by this simple analysis. Exact analysis has been done following the energy principles. We are not going to talk about it, but I would like you to note some of the results which you may find useful later. Here the T is expressed in the form g theta a cube b into a constant k. Similarly, the stress at this point, which is nothing but tau yz stress, and it is really maximum stress there, it can be written as T by j into k1 into a, and that is equal to sometimes written as T into another constant k2 by a square b, and this j is given in the form k a cube b. For various rectangular cross sections with b by a varying like this, the constants are going to change, which are shown here. So, b equal to a, this constant k2 which is here is equal to 0.6, and as the section become longer in the vertical direction, you are going to get this constant gradually reducing. And for infinity, this constant is equal to 3/8. We will like to use this result later. One point worth noting here is that the stress that we have obtained, tau yz stress, it is proportional to x. So, therefore, as the distance from the origin or the center of the cross section increases, so if we consider the section here, as the distance increases, the stress increases, and it is going to be highest at the outer periphery. You will find similar picture that if you calculate tau xz stress, it is going to be highest there, and it is going to vary linearly from this point to that point, and the maximum stress is acting at this point. However, this maximum is lower than the maximum here, that is why this is the most critically loaded point. We will try to look into more of physics little later. Let us introduce some analogy to understand the torsion problem. This is known as membrane analogy. It was introduced by Prandtl. You can do experiment to understand to determine the stresses in a section which is not circular and which is subjected to torsion. In the Prandtl's membrane analogy, let us consider a box, closed box, and in one of the face it has a cutout here. So, this is the cutout, and on this cutout is closed by a membrane. It could be a thin balloon material, sheet of balloon material, or it could be a soap film. Think of it that we have closed this cutout by a membrane or a soap film. So, it is very thin membrane indeed. If you now consider, therefore, the box has become now sealed or airtight. Now, if we try to increase the pressure here, the membrane is going to deflect, and it is going to be deflected like this. If you look from this side, it is going to be having a shape like that. There is deflection of this membrane from the undeformed state. Now, this deflection of the membrane, we will try to derive what sort of equation is satisfied by this deflection. To understand the or to get the governing equation which is involved, which involves this W displacement, let us concentrate on a small element here, which is delta x by delta y. I would like to now draw this element to a larger scale. So, this is delta x, this is delta y. This membrane is stretched along the boundary. So, it is attached to this boundary and it is also stretched, and that stretching per unit length of the boundary, let us say that is equal to capital S. So, the tension per unit length of the boundary. So, S is tension per unit length. Obviously, the membrane is going to be under pressure and the pressure will act normally to the surface, and the deflection of the membrane is very small. So, therefore, we can assume that this pressure is almost acting vertically. Therefore, the picture that we have here, we have tension all over the boundary, and since the deflection is very small, we can consider that this tension is unchanged per unit length. If we now consider the forces in the vertical direction, let us also try to write one more information, that if I look from the bottom to top direction or from origin towards y axis, then the deflected membrane shape is going to be like this. So, therefore, we have the traction, or rather the tension S is acting like this, here it is acting like this. Now, let us say that the slope of this is the slope here, and this is delta W, delta x is the slope, and now as we move to this one, there is a change in slope, and let us consider that this slope is equal to delta W delta x plus the rate of change of delta W delta x with x, or delta W delta x, delta 2 W delta x square multiplied by delta x. So, therefore, the slope here, let us say that this slope is like this. So, now if we try to write the forces in the vertical direction, let us say that is the vertical direction equal to 0. What we have is the pressure is acting vertically upward, and that is nothing but P into delta x delta y. P is the pressure, and now this component which is acting on this part of the boundary, which is delta y. So, this traction is acting on this part of the boundary, which is delta y. So, therefore, we can write now that S, and it is acting at an angle of this much. So, therefore, tan component of it will be approximately this. So, this multiplied by delta W delta x plus delta 2 W delta x square multiplied by delta x into delta y is the length of that span. So, therefore, that is the traction acting vertically, or the force which is acting vertically upward, minus S into this one, this is nothing but delta W delta x. Similarly, if we consider the other side, here we will have some forces coming due to tension per unit length, and here this will be also acting. So, therefore, if we consider that the slope here is delta W delta y, and the slope here is delta W delta y plus delta 2 W delta y square into delta y, then we can write from the other side that S if you would like to draw a sketch for it, we can do it that way. We have this, maybe we will draw it here. So, we have delta W, this is S, delta W, delta Y, and the angle here, this angle is going to be, so here this angle is going to be delta W delta Y plus delta 2 W delta Y square into delta Y. So, I am sorry that this has become little complicated, delta W delta Y plus delta W delta Y square into delta Y. So, now we can, this is acting on the face of length equal to delta Y. So, therefore, we can write S into delta W delta Y plus delta 2 W delta Y square into delta Y, and this is acting over the face of length delta x. So, therefore, delta x minus S delta W delta Y is equal to 0. So, therefore, I want you to note this, that this slope is delta W delta Y, and this slope here, this slope is delta W delta Y plus delta 2 W delta Y square into delta Y. So, once you simplify this, it gives us P plus S into delta 2 W delta x square plus delta 2 W delta Y square is equal to 0. On rearrangement, what we have is delta 2 W delta x square plus delta 2 W delta Y square is equal to minus P by S. Let us say that this is equation number 1. So, therefore, the deflection of the membrane that we were looking into, deflection of the membrane under pressure, you are going to have the deflection satisfying the function W, which stands for deflection, is going to satisfy the Laplace equation, because P is a constant, so also S, which is the tension per unit length along the boundary, is also constant. Therefore, this is going to be the equation satisfied, and it is nothing but it is Cauchy type equation. If you remember, the Prandtl stress function phi also satisfies an equation of the type delta 2 phi delta x square delta 2 phi delta y square is equal to minus 2g theta. So, these two equations are analogous, and therefore, it is possible to get an idea about the function phi by looking into the deflection of the membrane, provided the geometry of the membrane boundary corresponds to that of the shaft that one is interested in. Just I would like to work on this equation number 1, and we can write from 1 delta W delta 2 W, I beg pardon, delta 2 delta x square if we write this twice g theta s by p w plus delta 2 delta y square twice g theta s by p w is equal to minus 2 g theta. So, herein what it means is that phi is equal to twice g theta s by p w. Herein all are constant, g is a constant, theta is also a constant, s is a constant, p is a constant. So, therefore, this phi is linearly related to w. By taking a membrane having boundary shape corresponding to that of a section one is interested in, it is possible to get the idea about the function phi, and hence one can calculate the stresses also. In fact, the stresses delta phi, stresses tau xz is given by delta phi delta y. So, therefore, it is also going to be related to delta w delta y. Similarly, tau yz is minus delta phi delta y. So, therefore, it is related to delta w delta x. So, membrane shape will give us the idea about the stress. We will now like to solve some problem and then get the little more acquaintance with this membrane analogy. So, let us consider by this analogy, let us try to tackle the problem of rectangular section, triangular section and also elliptical section. If you consider now a rectangular section, let us say this is the section. So, therefore, membrane is going to have this boundary, and if we now imagine the membrane to deflect, obviously the membrane is going to have 0 deflection along the boundary, and it is going to have maximum deflection at the center, and that shape you can imagine it is a doubly curved surface. So, we can imagine that this is the shape of the surface, and we certainly have the maximum deflection at the center. If you are trying to consider this direction, let us say that is x direction, and let us consider the y direction to be like this. It is not difficult to see that this is really the maximum deflection, and let us say that this maximum deflection is equal to phi 0. If we approximate this curved surface by a straight line, if we just approximate it, so therefore, the slope here is going to be given by this angle. If you consider that this side is equal to 2a and this side is equal to 2b, then this slope is equal to is really negative slope. So, this is the slope, and this slope is equal to minus phi 0 by a. So, this is the height phi 0. It is proportional to w, we have written directly phi. So, therefore, this is phi 0 by a, that is the slope. And now we know that the shear stress which is going to act parallel to the boundary, which is nothing but tau yz is equal to minus delta phi delta x, and we get that delta phi delta x is nothing but this slope, and therefore, it is equal to phi 0 by a. So, this is the value of the stress which is going to act parallel to the boundary. Now, if you consider the curve here, the slope that we are going to get by joining the tip and this point, this is the slope. So, therefore, this is the slope, and hence the slope at the end of the y axis, let us consider that this is point number B. So, slope at point B is equal to minus phi 0 by B, because this height is equal to this distance is equal to B. The stress which is going to act here is parallel to this boundary, and it is nothing but tau xz stress. So, tau xz is equal to delta phi delta y, and we have found that this slope which is given by this angle is nothing but minus phi 0 by B. What it means is that the stress cannot act in this direction, it is going to act in this direction only. So, therefore, that is not the direction which is correct, and if the torque on this shaft is acting like this, we know for sure that this stress here it should be acting in that direction, and the stress here should be acting in this direction, and we have got the values correctly. So, therefore, herein without any difficulty you can understand that if B is less than A, we are going to get this slope to be higher than this one, and hence higher stress is going to act at this point, and the stress is going to vary linearly. In this case, you see that slope is maximum there, and it is gradually becoming 0 at this center. So, therefore, the stress is going to vary gradually from the, and in fact, it is a quadratic curve, it is going to vary linearly up to this center point to 0. Similarly, here the stress is maximum, and it is going to vary linearly to 0 at the center. So, we found that the stress is going to be maximum at this point B. Let us say that this point is A. Herein higher stress is going to act at the point which is closer to the center. It is different from the circular cross section, wherein you have found that the stress is going to be highest at the furthest point. We would like to do little more calculations to see the value of these stresses in terms of the applied torque. So, this doubly curved surface that we were talking about, let us approximate by a pyramid. So, let us approximate this doubly curved surface by the pyramid whose faces are this triangle, then this, and finally this triangle. And this height, we have indicated this thing as phi 0. Let us consider that height is equal to phi 0. The volume bounded by the approximate surface and the cross section, volume is nothing but, it is 1/3, the base is 4 AB, height is phi 0. We have already seen that the torque capacity is nothing but twice the volume bounded by the surface, phi surface and the base. So, therefore, it is 8 by 3 AB phi 0. So, we have phi 0 is equal to 3 by 16 T by AB. I am sorry, it is 4 by 3, this is 4 by 3. So, this will become 3 by 8 T by AB. Now, the stress at the point B, we have got that tau xz at B is equal to, it is T by, now that if I am showing the stress to be acting like this, it is positive stress, and therefore, this stress is equal to T by I beg your pardon, that is nothing but phi 0 by B. So, if we do calculations, it becomes 3 by 8 T by AB square. When A is very large, A is very large. In fact, the stress, so when you are trying to think of that this cross section is elongated in this direction, it becomes a narrow cross section like this. So, here in A is very large compared to 2B, then you are going to get the maximum stress at this location, and that is this value tau xz maximum is equal to 3 by 8 T by AB square. And if you have the cross section the other way, that this is the cross section. So, here 2B is larger than this, then the stress will become tau yz maximum, and that is just going to be phi 0 by A, and that will give us 3 by 8 T A square B. And in fact the exact value is 3 by 8 T by A square B. So, therefore, we have got really the value correctly obtained. I have given you a little while ago that the maximum stress in such cross section is going to occur here, and its magnitude is 3 by T A square by B. I would like you to look into triangular cross section and elliptical cross section. Triangular cross section, if you consider, so your membrane boundary is going to have the triangular shape as the shape of the bar cross section, and then we will find that the membrane surface is going to have doubly curved surface, and it can be approximated by a pyramid again for first approximation. So, this is the surface. So, we have approximated really the surface which is like this by this pyramid. Therefore, you can now immediately get the feeling that this is the CG of the triangle, and therefore, the maximum height is equal to phi 0 here. This is the, so this is the maximum height, And now if you consider the height of the triangle, the sides are, let us say, A. So, this is nothing but root 3 by 2 A, that root 3 by 2 A, and this distance you can calculate, it is going to be 1/3 of that, and the slope here is going to be easily available by considering this distance divided by this distance, and this distance is nothing but this distance here, it is root 3 by 2 A by 3. So, that is nothing but root 3 by 2 into root 2 into root 3, A by 2 into root 3, and you can calculate now the stress parallel to this boundary at this point A. So, if you consider that this is your y direction, so tau yz at A is nothing but minus phi 0 by the distance A by 2 into root 3. And you can obtain this phi 0 by considering the fact that torque capacity of the shaft is given by twice the volume bounded by this approximate pyramid, twice the volume of the approximate pyramid, and hence you can get this phi 0, and you can also obtain the solution approximately. For the elliptical section, if you consider the elliptical section, the surface of the membrane is going to be again doubly curved, and if you again if you just see the surface, it is going to look like this. That is the membrane surface, and it has the maximum height here, and therefore the stress is going to be higher because the slope of the surface is higher at this point, and therefore the slope is going to be higher, and it is lower at this point. In this case, you again note that this is the end of the minor axis and it is closer to the center, the stress is higher at this point. And in the case of the triangle, the stress is higher at this point. And now we would like to look into, you can really go on considering the problem of various types, various cross sections by this analogy, and you can immediately comment upon the point where the stress is going to be the maximum. Let us try to look into some points. I indicated earlier that for a rectangular cross section or a triangular cross section, the stress at the corner is going to be 0. Let us understand why that is so. The answer to this problem can be obtained 3 different ways. First of all, let us try to consider this rectangular section and let us concentrate at this corner. So, torque is acting like this. This is the axis of the shaft. If you consider this point, the stress is going to act parallel to this boundary in the same sense as the torque. So, therefore, we will have stress acting like this close to this boundary, and if we consider this boundary, stress is going to be acting like this close to this boundary. Now, at the corner, which is a common point, it has therefore possibility of stress acting in this direction and also in this direction. It is a single point and it cannot have two directions of the shear stress acting, and therefore from the uniqueness of the stress, the possibility is that this stress has got to be 0, both the stresses are going to be 0. That is from the consideration of this uniqueness of the stress. Now, I would like to give you the answer from the consideration of the membrane analogy. Then, if you now think of the membrane attached to this boundary and it is inflated from inside, the boundary deflection of the membrane is going to be 0 here, boundary deflection of the membrane will be 0 there in the direction out of the cross section. We know for sure that if the stress is going to act perpendicular to this boundary, this stress which is acting, so just concentrate on this element that located here, the stress acting on this area is going to be directed vertically upward, and that is again related to the slope of the phi surface in this direction, and since phi is 0 all along, the slope is 0, therefore this stress is 0. Similarly, if you now consider the stress, let us draw the element for clarity. So, let us say that this is the element. If the stress is going to act at this point parallel to this boundary, it has got to be directed like this. Now, this stress, it is obtainable from the slope of the phi surface in this direction, in the perpendicular direction. Since phi is 0 along this boundary, therefore again the slope is 0, therefore this stress is 0. So, this is from the Prandtl's membrane analogy. So, we can find the answer that the corner stress is 0 from the uniqueness of the stress at the corner point from the membrane analogy. Now, I will give you the third way of finding out the stress to be 0. Let us concentrate again on this element. If the stress going to be acting on this element on this face like this, then the stress which is going to act on this face, the opposite face, it is going to be like that, and the complementary shear stress will develop on the top surface, its direction has got to be like this. Similarly, on the opposite face, the stress direction is going to be like this. So, if the stress is to be non-zero on this face close to this boundary, then this stress has got to be non-zero, but we know that the surfaces, these surfaces of the shaft is free of any external loading, therefore this is 0, and if this is 0, this is also 0, so also this is 0, this is 0. So, therefore, this stress is 0. By similar type of argument, if non-zero stress is going to act at this point in this direction, then on the opposite face we will have stress acting like that, and the complementary shear stresses are going to act like this on this face, outer face. Since this outer face is again free of any external loading, this stress is 0, therefore this is 0, so also this and this is 0. So, therefore, we will find that the stresses are going to be 0. So, corner stresses, the same type of argument can also be considered for the triangular cross section. We will find that for that matter any corner is going to be free of any shear stress in a torsion problem. So, note that the stress at the furthest point, which is the corner, is 0. In the case of the circular shaft, we have found that the stress is going to be maximum at the furthest point, but in such cross section it is different. The stress at the furthest point, if it is a corner, it is 0, and if it is a point here somewhere there, the stress is maximum, but then high stress occurs at a point which is not the furthest, it can be at a point here which is at a distance shorter than this distance. So, the stress acting parallel to this boundary, if this is longer side than this one, then it is going to be higher than the stress acting at this point. I would like you to now see some of the cross sections which are shown here. Think of this case, already we have got the idea that the stress is going to be highest at this point, and from the membrane analogy you certainly can conclude on that. If you look into the membrane surface for this sort of boundary, we will have the surface looking from this direction and the surface looking from this direction. In the horizontal direction it will look like this. So, this is the membrane surface. So, the height here and here is the same, and since this distance is small, we are going to have higher slope. This slope is higher, and therefore the stress is going to be higher at this point than this point where the slope is given by this angle. So, if you consider that this is, let us say, alpha 1, this is alpha 2, since alpha 1 is greater than alpha 2, you are going to have this stress at point A. So, stress at A is going to be higher than stress at B, if of course the direction of the shear stress is like this, provided we have a torque like that. Now, concentrate on a cross section like this. So, if you have the T cross section, imagine that the membrane is deflecting, we have the torque direction like this. So, where do you expect the highest deflection of the membrane to occur? Obviously, it is going to be somewhere over here. And if you now try to look at the section, let us take a section here of the membrane surface. So, at this point it may typically look like this, that is the membrane surface. And if you consider a section there, let us say 1, the membrane is going to have deflection like this. So, therefore, more deflection at this point. So, this is for 2 and this is for 1. Similarly, if you look in this direction, if you take a intersection of the membrane surface with the vertical plane passing through this line, it may look like this. So, you have the maximum deflection here, this is phi 0, and here it is again phi 0. And immediately you can decide that the stress is going to be acting like this at this point, and it is highest. And obviously, the stress at this point is lower than the stress at this point, and it is going to act like this. And you will find also the corner stresses are all zeros. I leave it to you for consideration, and also look into a cross section like this, I cross section, and try to think about the stresses that are going to come up at various points on the boundary.